Hello, here's another problem. This problem covers Griffith's Chapter 1 only up to section 1.3. So this is about probability distribution. So this is a really good warm-up problem for stuff that you're going to be doing a lot in quantum mechanics. So this problem is about a Gaussian distribution. So the problem says to consider a Gaussian distribution, and this is a Gaussian probability density. So this would be the sort of distribution or limiting function that you get for things like test scores. This is your bell curve that you've probably heard a lot. You know, if you get a high enough sampling of something, then usually the value is going to reduce to a bell curve. So like if you measured the height of everybody in the United States, you get something, you'll end up getting a bell curve. Now, part A says to determine this constant here. That's a normalization constant. Part B, we want to find the expectation value of x and the expectation value of x squared. And that's leading towards finding the standard deviation. And then part C asks you to graph it. So I'm actually going to start with part C because I think that's going to make the other things that we're doing a little bit more clear, and I'll probably keep referring back to this. So like I said, this is a bell curve. This is an x, and this right here is rho of x, so it's a function of x. And the picture that it's going to make is going to look like a bell, and it is going to be symmetric by definition. Okay. Some of the numbers that we're going to be interested in is this, which is the amplitude, and then the center. So this is the part that is exactly in the center, and that's up here is going to be the highest amplitude. The other thing that we're going to be interested in is the width. So what is the spread of this? Okay, so first off, if we consider, what is the total area under this curve? So if you're familiar with calculus, which if you're taking this as a class, I really do hope you are, the area under the curve is going to be the integral from negative infinity to positive infinity in x of our function. Now we want to do something that's called normalizing, because like say these were test scores, or this was the average height of everybody in the United States. This area under the curve number can be really anything, but for convenience we want it to equal 1, corresponding to 100%. And if we set that equal to 1, that allows us to find a value for A. A here is going to be the amplitude, the highest point that it's going to be reaching. This amplitude is totally determined by the area under the curve. So we want to set the area under the curve to 1, so it is normalized, and then we find A, and A is our normalization constant. So this is something that we're going to be doing. This is going to be usually like your first step when you're considering, say, a particle in a well. You can always look up what the integral to a Gaussian is, but just to make your life a little bit easier, one thing that you usually want to do is do a U-substitution. So we can define U as equal to x minus a, and then we take the derivative du will be 1 dx. So because the derivative of x is going to be 1 there. So if you, and then our limits are going to stay the same, negative infinity to plus infinity. If you're not so familiar with how to do U substitutions and you're starting quantum mechanics, I suggest you brush up on them because it's very helpful. Okay, so then I have a 1 equals a. I can pull a out of the integral because it's a constant. We're going to go from negative infinity to positive infinity. My dx equals du. I have e to the minus u squared. And then you can find this in any integral table. And what you're going to get is the a coming out there. And that's just going to equal square root of pi over this other constant lambda. We solve that for a, and we get that a equals square root of lambda over pi. So that's our answer for part A. Our normalization constant is going to be a over square root of pi. So as long as I put that into my function, then my function is normalized. So it will look like this. And then e to the lambda. Okay, now part B. So actually, let me just go ahead and fill that in here so we can come back here and just fill in our graph. So that means that the highest point that this can get to is a square root of lambda over pi. And if you get confused, oh, was it pi over lambda? Was it lambda over pi? You can always check the units on it too. And when you're dealing with the physical constant. Okay. Now, part B is getting towards finding the standard deviation. The method of getting you there is to find the expectation value of x and the expectation value of x squared. So first we go to find the expectation value of x. Unlike problem 1.1, we don't really want to find this by hand because that's just not going to be possible to do a summation because this is a continuous variable. So what we're going to do is we are going to find it and taking that constant out by taking that integral of x times our probability distribution. Now again, to make it just a little bit more easier, we can do our U-substitution. And then du is going to equal dx. Our limits of integration don't change. So my expectation value of x is going to equal this lambda over pi integrating du, and then that's going to be u plus a times negative lambda e to the u squared. Okay, again we can, we don't have to actually solve anything again because we can come out here and we can just break this into two integrals. So we will have du u e to lambda squared, and then that will be plus, since a is a constant, we can pull it out of the integral and we'll have the same integral there. I'll write it down here. So that would be plus this, oops, and then an a. That's not part of that square root. And then over here we have the same integral from part A, which we know the answer to. And this guy we can also find in an integral table. Or you could work out the integral yourself, there's certainly no problem with that. So what we get is the expectation value of x equals, this is always coming out there, that integral, so just kind of a hint there, when we had u times du u, so we have even function, odd function with equal parts negative and positive, which means it's 0. Because now it's, so even function times an odd function is odd. An odd function over all space is the sum is going to be the 0, so the integral is going to be 0. And then for that second integral we get that constant a, and then we got what we got exactly in the first part, which was square root of pi over lambda. We distribute this guy in and we get a. So that means that the expectation value of x, or the average of x, is a. So the average is the part that's in, is going to be our average value here. So our Gaussian is of course going to be centered around its average, and its average is a. So now the last thing that I need as far as this, important information on my graph I want to fill in, I found the amplitude, I found the average, now I want the width. And the width is, how much it varies, like we saw before with delta j, how much difference there is between the calculated value and the measured value. So in that case it's going to be how wide the Gaussian is. To do that I want sigma. To find sigma I need the expectation value of x squared. And here's kind of a spoiler. For x squared we're going to have even times even, so that's not going to be equal to 0 because it's going to be an even function. Okay, I'm going to do the same U-substitution idea again. This is going to equal lambda over pi, and then it will be dx x squared x minus a. Doing the same exact U-substitution, and then kind of parsing it out. So to do the U-substitution, what I'll have is u equals x minus a, x equals u plus a, x squared is going to be this, which is going to be u squared plus 2au plus a squared. So I'm just going to write all those out. So I have du u squared e to the negative lambda u squared plus 2, we can just put that in brackets because they're all going to be times that, plus a 2a du u lambda u. That of course is going to be 0, and then because it's not symmetric, and then we have an a squared du e squared. That of course is going to be a squared times pi over lambda, which we know from what we got the first time. And the first integral is just going to, so this guy from negative infinity, positive infinity, u squared. So that's an even function. This is something you can find from an integral table. And this one is going to equal 1 over 2 lambda. So that's going to be the a squared. Well, it's once we multiply it all out, that would have that guy in there as well. So once we multiply out the constant through there, this is what we get for this. And I said this you can find from an integral table or using Mathematica or the software of your choice there. So then sigma squared is going to be the expectation value of that squared minus this. So what we get is this guy that we just computed, and then minus the average, which was a squared. So that means sigma squared equals 1 over 2 lambda. So our standard deviation is 1 over square root 2 lambda. Okay, so then we can go back to, so that's part B. Now we go back to part C. And our width we have now found. And because our width is sigma, so that value is 1 over 2 lambda. So this kind of tells us something very nice and fundamental about our Gaussian. So instead of writing it like this, what we have found is that this is the average here. That's where it's centered. And our sigma equals 1 over square root of that lambda. So our lambda equals, let me just do out this algebra real quick. 1 over sigma, we square that both, so we get 2 lambda 1 over sigma squared, so our lambda equals 1 over 2 sigma squared. So we can rewrite this all out. We can have it normalized to pi over lambda, or we can write that as pi over 2 sigma. Oops. So that would be lambda in the denominator there, which brings it up to the top. So we have 2 pi sigma e to the negative x minus x average, and then that's all over 2 sigma, the standard deviation. And there is a very nicely normalized Gaussian function, which is useful for a whole bunch of applications. But the even going beyond quantum mechanics. But those techniques that we used are really going to be useful when we start looking at solving for wave functions and normalizing them.